Maths Unbound. Scarily, large numbers can quickly grow from humble beginnings, as the old word and chessboard problem demonstrates. The earliest recorded version of this appears in the writing of Islamic scholar Ibn Khaldun in 1256. According to the tale, King Sirham of India wanted to thank Grand Vizier Sisa Bendahir for his invention of the game of chess and asked Sisa what he'd like as a reward. Sisa's request seemed pitifully modest: 1 grain for weight for the first square of the chessboard, 2 for the second, 4 for the third, and so on, the amount doubling each time until all the squares had been covered. The king, thinking he got off lightly, immediately granted the wish, but then soon regretted it. The total amount of grains needed turns out to be 1 plus 2 plus 2 square plus 2 cube until plus 2 the 63 equals a number far greater than all the word grains in the world. King Sirham learned a couple of lessons for his encounter with the crafty Grand Vizier. First, he found out about the surprising power of repeated doubling, or more generally, more generally that of exponentiation, in which a number is multiplied by itself over and over again. And second, it was brought home to him that maths isn't confined by practical considerations. Physical limits don't restrict the world of the mathematician. On the contrary, this world is big enough to contain anything and any number we can imagine. Among the most interesting and important numbers in maths are prime numbers. Their distinguishing feature is that they're divisible only by themselves and 1. The first ten of them are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Gradually, as they get larger, the gaps between them tend to widen. For example, after 1000, the first 10 are 10,009, 10,009, 10,013, 10,019, 10,021, 10,031, 10,033, 10,039, 10,000. The first 10 are 1009, 1013, 1019, 1021, 1031, 1033, 1039, 1041, 49, 1051, and 1061. It's easy to prove that there are infinitely many prime numbers, but what particularly interests mathematicians is how they are distributed, but details of the way in which they thin out at the larger and larger values. One of the greatest unsolved problems in math, the Riemann hypothesis, is intimately concerned with this very issue. There are also practical reasons for seeking out bigger and bigger primes. More importantly, very big primes are crucial to the most widely used systems for encrypting data, such as those that underpin all online banking and shopping. The easiest to find primes are those that happen to be Martian numbers, after, out, named after French prior and polymath Marie Mersenne, who studied them in the first half of the 17th century. All Mersenne numbers can be expressed in the form 2 to the n minus 1, where n is a positive integer. In other words, they are there are one less than corresponding power of 2. The first few are 1, 3, 7, 15, 31, 63, and 127. For small values of n, whenever n is prime, the corresponding Maxent number is also prime. For example, when n equals 7, 2 to the n minus 1 equals 127, which is prime because it has no factors other than 1 and 127. But this pattern breaks down for n equals 11 because 2 equals 11, 2 to the 11 minus 1 equals 2047 equals 23 times 89. Mathematician now that although is the case of every Maxent prime, n must also be prime, other conditions have to be satisfied as well. Fortunately, these extra conditions are easy enough to be coded into a program so that computers can crunch their way through relatively simple, fast algorithms in the case for the next bigger Maxent prime. The process of finding them can be used as a way of testing the speed and capability of new, faster computers and algorithms, the step-by-step methods used to solve problems. It also comes in handy as a marketing ploy for these new machines because the appearance of a new, largest non-prime tends to make front page news. One of us had some One of us, David, had some personal experience of this. The late 1970s, I worked for the Minneapolis-based supercomputer manufacturer Cray Research in the applications development group. One of our tasks was to show how much quicker than the Cray-1, than the world's fastest number computer, was than any of its rivals. In this, we were helped by the efforts of a young software engineer, David Slowinski. I had the opportunity to meet David on a number of occasions, and he explained to me how his Maxent prime hunting algorithm worked. He and Harry Nelson, a mathematician at the Lawrence Livermore National Laboratory, were one of the earliest K1s was undergoing acceptance tests, had optimized the algorithm to run on the Kray's unusual vector architecture. In April 1979, Slowinski and Nelson's efforts were awarded with the discovery of the 27 Maxent prime 2 to the 44,497 minus 1, the largest prime number known at the time. This also gained them a place in the Guinness Book of Records. Slowinski went on to discover 6 more record-breaking primes between 1982 and 1999, culminating in 2 to the 1,257 to 1,257,787 or M 1,257,687. The 34th Maxent prime, which he found in collaboration with computer scientist Paul Gig using a Cray 390 supercomputer. Of the 10 largest prime numbers found to date, 9 are Maxent primes. The current champion at the time of writing, discovered in January 2018, is Written out in full, it has close to 25 million digits, enough to fill several volumes of the last print edition of Encyclopedia Britannica. Mersenne primes can be used to find another kind of interesting number known as perfect numbers. A perfect number is a whole number that is equal to the sum of all its factors, except itself. For 6 is a perfect number because its factor 1, 2, and 3 add to give 6. The next smallest is 28, the sum of 1 plus 2 plus 4 plus 7 plus 14. In about 300 BCE, Euclid proved that whenever 2 to the n minus 1 is prime, while n itself is prime, is another words formation prime formation formation prime minus 2 to the n minus 1 times 2 to the n minus 1 is an even perfect number. For example, these four perfect numbers are generated like this. All even perfect numbers end in 6 or 8 and have a corresponding Mersenne prime. There are no noun or perfect numbers. So up to the present, there's a one-to-one correspondence between non-Mersenne primes and non-perfect numbers. The largest non-perfect number is that corresponding with the largest non-Mersenne prime. It has value written out in full. It involves just under 50 million digits. So to avoid losing readers, we'll just show how it starts and finishes. Strangely enough, although we know that there are infinitely many primes, we don't know if there are infinitely many Mersenne numbers. Likewise, we don't know if there are infinitely many perfect numbers or if there are any odd perfect numbers. In any event, it's easy to come up with a number that's bigger than the biggest prime or perfect number just at 1. But large numbers that have some features like of interest other than being simply big hold a special fascination. Sometimes the large number in question marks the earliest point at which some mathematical condition is satisfied. This is the case with the Skews number, named after South African mathematician Stanley Skews. Like the Riemann hypothesis, to which is related, Skews number has to do with the distribution of primes, born in Transvaal to an American-born mother and an English father in 1899. Stanley Skews to a degree in civil engineering at the University of Cape Town before heading to Cambridge to study mathematics at King's College, where among his contemporaries and growing partners was Alan Turing. He studied for his BA, MA, and finally PhD. His doctoral supervisor, John Edenshaw Littlewood, was an eminent number theorist and close collaborator of G.H. Hardy, who brought to Indian genius Ramanujan to England. It was Littlewood who encouraged Skews to pursue research into prime numbers. Mathematicians had searched long and hard for a formula that would generate prime numbers without success. However, they had found that the occurrence of primes isn't haphazard, rather there are rulers governing their distribution. Their density decreases when moving to larger numbers. A result known as the prime number theorem was first proposed by German mathematician Carl Gauss in about 1792 when he was just a teenager. However, it wasn't until 1896 that it was proved independently by French mathematicians Jacques Hadamard and Charles de la Vallée-Poussin. According to this theorem, the density of primes around any number x is approximately 1 over log ex, when log ex is natural logarithm of x. So around 100, we'd expect about 1 in 5 numbers to be prime, whereas around 1000 this falls to about 1 in 7. The prime number The prime number theorem makes it possible to estimate how many primes there are less than any given number n. In fact, for larger values of n, the value predicted by the theorem is remarkably close to actual number of primes. For example, there are exactly primes less than 1 million, whereas the theorem predicted as a value of just 1000 just 1700 or 701 or 0.0033% more. The estimated value from the prime number is consistently a little bit higher than the actual number of primes, even when n is the enormous. In the absence of evidence to the contrary, mathematicians assume this would always be the case without exception, but then Littlewood came up with a proof that at some point the overestimates will stop and underestimates will take over for a while before there was a switch back to overestimates and so on, back and forth forever. Littlewood didn't know when the first crossover would happen. However, his student Skills managed to shed some light on this question. Skills showed that the prime number theorem must split to giving underestimates before n reaches the value of the before n reaches the value. This spectacularly big number, Skills number, assumed that the Riemann hypothesis is true. The Riemann hypothesis effectively says that prime numbers are just about as organized and predictable as it's possible for them to be given their nature. Skills calculated that if the hypothesis were false, then the prime number theorem would first switch to underestimating the number of primes when n was even larger about, which became known as Skill's second number. G. H. Hardy once described Skill's number as the largest number which has ever served any definite purpose in mathematics, although it's long since lost the distinction it immense since size does underscore an important point that just because something has held true as far as anyone has managed to test it doesn't guarantee it'll be true in every conceivable case. This is one of the reasons mathematicians are never happy until they've found a proof that rigorous proof that will stand for all time. Since Gibbs published his results, the lower and upper bounds, depending on whether Riemann's hypothesis is assumed to be true or not, has been drastically reduced. For the first half century or more, computers have been used in these calculations. In 1966, American mathematician Sherman Lehman showed that somewhere between the values of for n of 1.53 times 1 10 to 1165 and 1.65 times 10 to 1165, there are more than 1 to the 10 to 500 consecutive integers from which prime number theorem estimates the actual number of primes up to that point. No one's yet identified a specific number where the crossover first happens. The most recent work published on the subject by Stephanie Zegowitz of the University of Manchester in 2010 found that the first time the prime number theorem gives an underestimate is for some value n that's less than 1.3972 times 10 to 360, although still big by everyday standards. This value is minuscule compared with the original skew number. Other gigantic numbers in math emerge from problems to do with combinations and probability. Take an ordinary pack of playing cards. How many different ways can the deck be arranged? The first card can be any 52, the second any of the remaining 51, and so on, so that the total of number of possible arrangements is 52 times 51 times 50 until times 3 times 2 times 1. This is known as 52 factorials. Factorial written out in full it turns out to be. Or in scientific notation, approximately 8.0658 times 10 to 67. If a deck had been randomly shuffled every second since the start of the universe, there would have been time for only about 4.32 times 10 to 17 shuffles, a significant proportion of all the different ones possible. It's fair to say that any story about a random shuffle having produced a perfect ordering of deck isn't true. The odds are are, are 80 million trillion to 1 against. Such claims generally mean that someone is priming on the shuffle wasn't truly random.
Chess offers even more possible combinations. American mathematician and electrical engineer Claude Shannon, often referred to as the father of information theory, was fascinated by the link between chess and the emerging new field of computer science. On 9 March 1949, he presented a paper called Programming a Computer to Play Chess at National Institute for Radio Engineers Convention in New York. In this, he argued that the number of possible positions that any legal number of chess pieces could be in at a given point in a chess match was between 10 to 43 and 10 to 50. He also estimated that the number of possible games two players could play without repeating themselves, the so-called Shannon number, was around 10 to 120. Of course, this includes all kinds of games that would never happen in practice unless one of both players had a clue what they were doing. The number of realistic games between players who have at least rudimentary knowledge of the game and manage to avoid ridiculous move combinations is much lower, but still immense. The Shannon number, or more formally, the game theory complexity of chess, is so huge. Shannon realized that for computers to be successful in competing with humans, their programs couldn't be based simply on analyzing every possible position from the outset. Other familiar games have their own game theory complexities. Tic-tac-toe, also known as noughts and crosses, is obviously much simpler than chess. Nevertheless, it can give rise to a surprisingly large number of game situations. For the first player can put a O of X in any one of 9 places. The second player can choose from the 8 remaining places, and so on. Continuing this line of reasoning gives a value of 9 factorials. 9 factorial equals the 362,880 for the upper bound of the game tree size. But this number includes many illegal situations, since the rules say that the game ends as soon as one player achieves a line of three O's of X's, so that not all 9 squares have to be filled in. The number of possible legal games turns out to be 255,168 or a mere 26,830 if reflections and rotations of positions are treated as being identical. The popular game of Connect 4 is much more complicated than tic-tac-toe. It's played using 6 up by 7 across vertical board and 2 sets of color counters. The winner is the first to make a line of 4 counters of the color. Altogether, there are different board positions and about 1.1 times 10 to 20 possible game situations. Backgammon is much more complex than Connect 4. In fact, the number of possible games of backgammon is about 10 to 144, far greater than the number of possible chess games, even though there are many more possible board positions in chess than backgammon, a vastly more complicated game than any with cat mentioned in his book, invented in China some 2,500 years ago. It's most commonly played on a square grid made up of 90 times 90 lines. 19 times 19 lines. 2 players, black and white, taking turn to place stones of their color at the intersections of the lines. Although the rules are simple, the strategy needed to play well is finely hard. Go is estimated to allow about 10 to 172 both positions and about 10 to 360 different games.
If the universe is considered to be made up of many tiny cells of subatomic-sized locations, each of which can be in a variety of different states, then we can think of it as being like a colossal board game. This brings us back to the concept of Poincare recurrence times, which we talked about in the last chapter. In particular, if the cosmic game is played on a board with cells that are Planck unit wide, and with the smallest particles in nature than the time. In years needed for the board position to return to a particular state in the first number we mentioned that was calculated by Don Page. The problem of figuring out the probability of a complicated system reaching a specific state has cropped up in various cases over the centuries. A classic thought experiment dating back more than a century involves monkeys and typewriters. It was discussed as 1913 by French mathematician Emile Borel, and perhaps by others even before that. A common statement of it is how long would it takes it how long it would how long would it take a monkey hitting the keys of a typewriter at random to type out Hamlet word for word exactly as Shakespeare had written it. Obviously, most of what the monkey would type would be utter gibberish. Even coming up with a very three-letter English word would be a rarity. The first line of the play, spoken by Bernardo, is "Who's there?" The chance of the monkey hitting the W are 1 in 44 because there are 44 keys as on the standard typewriter keyboard. The chance of hitting H immediately after the W are also 1 in 44, so that chance of hitting the circles of WH are 1 in 44 times 44, or 1 in 1913, or 1 in 100, 1936. The odds of our hypothetical simian getting the first word of Hamlet correct on any given attempt are pitiful 1 in 44 times 44 times 44, or 1 in 85,184. Next, it has to hit the apostrophe, then the S, then a space. You see the problem. You'd have a better chance of winning Euro millions, and we haven't even started on the second word. What's more, if the monkey makes a single mistake, all its efforts are undone and any correct sequence is managed to produce up to, to that point has to be thrown out and fresh start made. Hamlet, the longest Shakespeare plays, contained 30,557 words and approximately 1,030,000 letters, punctuation marks, and space between words. The odd, the, the odd of typing, the odd of typing incorrectly in one go using random keystrokes about 1 in. Assuming that capital letters are separated keys, 1, an actual typewriter, capital letters, and some punctuation marks require the simultaneous pressing of two keys, the shift key plus one other, which vastly diminishes the probability of success. The fact is that even if the universe were crammed full of subatomic-sized monkeys that had been tapping away non-stop on the subatomic-sized typewriters since the Big Bang, there'd be only a 1 in a trillion chance of them typing even the first 79 characters of Hamlet correctly. Of course, real monkeys are inclined to spend their days working diligently without break as typists, even of the hit or miss variety. This fact, this fact was borne out when, in 2003, as a piece of performance art, a computer keyboard connected by a radio link to a website was left to enclosure of 6 Sulawesi crested macaques at Panton Zoo in Devon. The animals could watch the result of their efforts on the screen. While the novelty of their new plaything lasted, the monkeys managed to produce 6 pages of writing, consisting mostly of the letter S before. In the fit of rage, the alpha male attacked the keyboard with a stone and the others ended up urinating on it. In 2011, American programmer Jesse Anderson enlisted the help of an army of virtual and more compliant monkeys to recreate not just Hamlet but all the Shakespeare's works. Using Amazon EC2 cloud computing system, he ran millions of small computer programs simultaneously, each churning out random sequences of 9 characters. However, it was a much watered down version of the original Monkeys and Typewriters challenge. Anderson required only that a 9-letter sequence appear anywhere in the batch writings for it to be checked off as completed. It doesn't compare with the feat of having to get all the letters and other characters correct for Hamlet in one go. On the upside, as Anderson pointed out, this is the largest work ever randomly reproduced. It is one small step for a monkey, one giant leap for virtual primates everywhere. A similar concept to that of the monkeys and typewriters has been explored by writers such as George Louis Borges. In his 1941 short story The Library of Babel, Borges imagines an immense library containing a vast number of books, identical in size and format. Each book contains 410 pages. Each page 40 lines, each line approximately 80 black letters. Only 22 alphabetic characters, plus a comma, full stop, and space are used throughout, but every possible combination of these characters that follow the common format occurs in the sum book of the library. Most books appear to be just a meaningless jumble of characters. Others are quite orderly but still devoid of any apparent meaning. For example, one book contains just the letter A repeated over and over. Another is exactly the same except that the second letter is replaced by a B. Others have words, sentences, and whole paragraphs that are grammatically correct in some language but are nevertheless illogical. Some are true histories. Some purport to be true histories but are, in fact, fictional. Some contain descriptions of devices yet to be invented or discoveries yet to be made. Somewhere in the library is a book that contains every combination of the basic 25 symbols that can be imagined or written down in the given format. Yet all of it are useless because, without knowing in advantage what's true or false, fact or fiction, meaningful or meaningless, such exhaustive, such exhaustive, exhaustive combinations of symbols have no value. How big would Borges' library be? Jonathan Basil of Emory University has simulated an English language version of it on the website libraryofbabel.info. An algorithm he wrote generates a book by iterating every permutation of 29 characters, the 26 English letters, plus space, comma, and full stop. Each book is marked by a coordinate corresponding to its place in the hexagonal library so that every book can be found in the same location every time. The website is said to contain all possible pages of 3,200 characters, about 10 to 4,677 books. This site also has a search tool with which users can find the whereabouts in the library of any known page of text. An individual page of Hamlet can be found in this way, though the probability of finding any other page from the same work in the same volume is next to zero. If a user clicks through the books at a rate of 1 per second, it will take about 10 to 460 10 to 4,668 years to go to the library. Essentially useless though it may be, there's something compelling about Basil creation. It contains every page that has ever been written or ever will be written within the limits of its format. Every news story, past, present, and future, every play and novel, every work of fact and fiction, including this book, and every scientific discovery that will ever be made, somewhere within it, along with much that is meaningless or false, like accurate descriptions of every planet across the first reaches of space and time, and the true details of how life and the universe itself originated. We've already come across some impressively large numbers, and it's time to start thinking about how we might represent even larger ones in a convenient, manageable way. The only mathematical operations we normally use for dealing with numbers and are addition, multiplication, and exponentiation. Adding is just repeatedly Addition is just repeatedly adding one to some starting number. In other words, counting up one at a time. If the starting number is 8 and we want to add 4 to it, we can write this as 8 plus 4 as 8 plus 4 ones. 8 plus 4 equals 8 plus 1 plus 1 plus 1 plus 1 equals 12. Multiplication is repeated addition, so that for instance 7 times 4 equals 7 times 7 times 7 times 4. 7 times 4 equals 7 plus 7 plus 7 plus 7 equals 28, and exponentiation is repeated multiplication. For example, 3 to the 6 equals 3 times 3 times 3 times 3 times 3 times 3 equals 729. For most practical purposes, we don't need any operation that's more powerful or compact in its notation than raising one number to the power of another, but we're about to venture it into realms that go far beyond the practical, so we'll need something that transcends our familiar ways of representing numbers. Let's start by writing down the operation of addition, multiplication, and exponentiation in a general form. In fact, let's start right at the beginning with something we don't often hear about, the successor operation. This gets us off the ground, mathematically speaking, starting from 0 and adding on 1, and then 1 more and so on. The simplest thing we can do is add 1 onto a number a to give the successive number a plus 1. The successor operation, at least in the form it's defined here, is the first thing we learn in mathematics, how to count up one at a time. Next step up is general addition, in which we repeatedly apply the successor operation. In other words, begin with number a and add on b once. We can write this as. Next, in multiplication, if we're multiplying a times b, we can set this out as. Finally, we can write a to the power of b as. Notice that each level of operation can be expressed in terms of the one immediately below. For example, multiplication in terms of repeated addition. In fact, it's just a compact way of thinking about and representing this low operation. For most purposes, we don't need to go beyond the a to the power of b exponential stage. The kind of big numbers we meet in everyday life, read about in the news, or for that matter, with which most scientists and mathematicians ever deal, can be represented comfortably in exponential form. The two richest people in the world at the time of writing are Jeff Bezos of Amazon, with about 190 billion to his name, and Bill Gates of Microsoft, with about $120 billion. That's only 1 or 2 times 10 to the power of 11 each. 10 to the power of $11 each. all the money in the world can be written very compactly as about 3 times 10 to 12 dollar 10 to the 10 to 12 US dollar. Each species and astronomers studying everything from subatomic particles to the cosmos as a whole can manage perfectly well with numbers in exponential form. We've come across a few numbers in this book, though which are too big to be written simply as one number to the power of another. The googolplex, for instance, is 10 to Google, but writing in this way is cheating, since a Google equals 10 to 100. We should really write it as using a repeatedly exponential. In the same way, if we think back of Skewers number and base cosmic recurrence time, this need a stack of powers in order that we can represent them without filling this book or entire universe with zeros, carets, or circumflex accents are commonly used to indicate powers and are handy device, especially if you want to avoid with typesetting problems. The trouble is you start dealing with numbers that are far bigger than the googolplex of Skew's number or even page cosmic recurrence time. It becomes unwieldy to show them like this, just as it's much easier to read and write 100 trillion as 10 to 14 as so with like a more conscience of so with like a more consist way of representing a gigantic number like, say, English mathematician Raven Goodstein, in his 1947 paper Transfinite Ordinals in Recursive Number Theory, coined the name tetration for the operation that was the next step up from exponentiation. The word combines the Greek tetra for 4 with iteration and conveys the fact that tetration is the fourth level in the hierarchy of operation after addition, multiplication, and exponentiation, just as we summarize exponentiation as. So we can summarize tetration as where B copies of A combined by exponentiation working from right to left. For instance, others, such as Nick Bromer of Bryn Mawr College in paper published in the 1987, have used the term superexponentiation instead of tetration, but the two words means exactly the same thing. Both refer to next operation in the sequence: addition, multiplication, and exponentiation. Most of us never come across superexponentiation or tetration. Neither, neither that for that matter do most mathematicians unless they happen to specialize in a field that involves having to deal with fantastically large numbers. But since this but since this a book specifically about big numbers, we'll need to get used to these strange terms. Coming up with meaningful names for big numbers and ways for defining them is part of the challenge of the subject we're talking about here. We also need to be careful about getting all our terminology accurate. For instance, Skew's number isn't a tetration because not all the exponents are the same. Instead, like the googolplex and base cosmic recurrence time, it takes the form, which is called an iterated exponential. It's also possible to have a number that looks like, where all the exponents are different, in which case it would be called a nested exponential. As we'll say later, there are other ways of notating titerations that allow an easy extension to even more powerful operations. After all, why stop at titration? If titration is repeated exponentiation, then repeated titration brings us to the next level of operator, which could then called pentation. Next would be hexation, and so on. Mathematicians refer to this sequence of arithmetic operations, succession, addition, multiplication, exponentiation, tetration, pentation, and so on as the hyperoperation sequence, and it goes on forever. Starting for succession, which is called hyper-zero, tetration is also known as hyper-4, pentation as hyper-5, hexation as hyper-6, and so on. Although we mention Reverend Godstein as having invented in the name tetration, he certainly wasn't the first to deal with the concept of the nomenclature of hyperoperators. The notion for a raised to the a n times was introduced by German mathematician Hans Maurer in 1901, although it didn't come to widespread attention until 1995 when Rudi Rucker wrote about it in his book Infinity and the Mind. As for the origin of ideas about operators more powerful than exponentiation, we have to go further back in time. The story really begins with Johann Lambert, an 18th century Swiss polymath who made an extraordinary number of important contributions to math, physics, astronomy, logic, and philosophy. He invented the first practical hygrometer for measuring humidity, came up with the nebula hypothesis for the origin of the solar system, and the gesture of model accepted today suggested correctly that the Sun is part of a group of stars, at the most collectively to our galaxy, and did pioneering work in photometry. In maths, he gave the first rigorous proof that pi is irrational, investigated the general properties of map projections, introduced hyperbolic functions into trigonometry, and speculated about non-Euclidean geometry. Lambert also defined something that's come to be known as the Lambert W function, otherwise called the omega function of product logarithm. He used it to solve problems that couldn't be solved at the time by any conventional means available, and the sample will be solving the equation 3x equals 3 to the x. There's no need to go into the intricacies of what the W function involves other than to say that it laid the basis of figuring out what happens when the number is raised to the same power over and over again indefinitely. Lambert wrote about this function in his first book, early enough on the subject of light passing to various media, published in 1758. However, it was his compatriot Leonhard Euler who used the W function in a way that links it to tetration via what's become known as the power to what function. Euler was 20 years older than Lambert, and among his prolific and among the most prolific mathematicians in history. In one of his papers, he referred to ingenious engineer Lambert, which sounds a bit like a backhanded compliment. Their mathematical interests overlap, especially in areas of number theory. Euler proved that E was irrational before Lambert proved the same about pi. Lambert's work on the W function led Euler to consider the properties of what became known as the power to what function, in which the axis is stacked infinitely high. A quick glance might suggest that For all values of x greater than 1, greater than 1, this function will shoot off to infinity. We're so used to using the term exponential growth to mean explosive growth that it seems in a repeated exponential like Euler's should just blow up without limit whenever x greater than 1. But remarkably, this isn't the case. There are many values of x greater than 1 for which Euler's power tower function converges to a finite value. For instance, if x equals square root of 2, then, and the value of this is easy to prove, is an infinity or some gigantic finite number, but just 2. In investigating his power toward function, Euler became a pioneer of hyperorganizations that lie beyond simple exponentiation. He was the first to look in depth at what we now call tetration, and although he recognized that raising a power to a power and so on could quickly lead to colossal numbers, he also turned up some surprises. The path to the path to the biggest number in the world isn't just recently upward but has fascinating twists and turns.